Hello everyone, welcome to ncert Physics Simplified. And in this video, I'm going to explain you article number 14.5. This is PN junction. And in the previous video, we have seen P-type semiconductor and N-type semiconductor. Now what we'll do, we'll just connect or join these two semiconductor, and what we obtain is a PN junction. Okay, so let's start ncert and see what is in the ncert. Okay, so a PN junction is the basic building block of many semiconductor devices like diode, transistor. Okay, so diode, transistor, we'll understand this, they are very important part in the electronic component. Okay, so this is the basic thing that is part of the diode and transistor. A clear understanding of the junction behavior is important to analyze the working of other semiconductor devices. Okay, so if we want to understand the working of semiconductor devices, we need to understand how junction works. Okay, what are the different aspects of this junction is, PN junction is. We will try to understand how a junction is formed and how the junction behaves under the influence of external applied voltage. So we'll just when important term is there is a bias. Okay, what is bias? So what we'll do, we'll apply external voltage to this PN junction, and we'll see how the voltage affects it, what is the current in that. Okay, so let's understand PN junction formation. Okay, so consider a thin p-type semi-silicon semiconductor wafer. Okay, so what we have taken, a p-type silicon semiconductor wafer we have taken. Okay, by adding precisely a small quantity of pentavalent impurity, part of the p silicon wafer can be converted into n silicon. So what we do, we have taken some pentavalent impurity and we have added to this silicon wafer. So as we know from the previous video, when we add pentavalent impurity, so it will become what? N-type semiconductor. So this is how we obtain PN junction. Okay, there are other ways to obtain PN junction. This is one of them. There are several processes by which a semiconductor can be formed. The wafer now contains P region and N region and a metallurgical junction between PN junction. So we have this is a P-type semiconductor and N-type semiconductor, and there is a junction between these two. Okay, so this is a PN junction. Okay, two important processes occur during the formation of a PN junction. These are diffusion and drift. So now what happens, there are two processes, diffusion. So now in P-type semiconductor what will happen, in P-type semiconductor, you have to recall from the previous video that in P-type semiconductor there are holes in this. Okay, and the majority charge carrier are the holes. Okay, and in N-type semiconductor there are majority charge carrier as electrons. There are electrons in this majority charge carriers, and in this P-type there are holes. Okay, there are minority charge carriers also, negative electrons in P-type, and N-type there are holes, but their number are very small. Okay, so majority charge carrier are the majority, they are the real charge carrier, you will see. Okay, now see, we know that in a N-type semiconductor the concentrations of electrons, number of electron per unit volume, is more compared to the concentration of hole. Okay, as we have discussed in the previous video, in an N-type semiconductor number of holes is far more greater than number of electrons. And in this is for P-type semiconductor, and that is the opposite cases for the P-type semiconductor. Okay, yeah. Now similarly, in a P-type semiconductor the concentration of hole is more than, I think I have made the opposite way, I have said this in the opposite way, but you have understood. Then in the P-type semiconductor their hole are greater, and in N-type semiconductor there are electrons are greater. Okay, you should keep this in mind. Now during the formation of the PN junction, and due to the concentration gradient across P and N sides, hole diffuse from P side to N side, and electron differs from N side to P side. So now what happens, as you know, there are electrons in the n-type semiconductor, and there are p-type. The concentration is large. So what will happen, this electron will be attracted to this hole, and they will move to this side. They will start diffusing, okay, to this holes. Okay, so this will give rise to diffusion current. Okay, a hole will start diffusing to this side, and electron will start diffusing to this side, and there will be recombination of electron and hole. Okay, and this will give rise to diffusion current. Okay, it will be a very short period of time when the junction is formed. When an electron diffuses from N to P, it leaves behind an ionized donor on N side. Okay, now remember very important point here. Now what is happening here? You see, electron is going here. Okay, electron is going here, and let me ask you a question here. Okay, this p-type and type, let them look separately. This p-type has majority charge carriers as whole. Okay, positive charges, that is. But what was the overall charge of this whole block, this p-type? Was it positive charge, the whole block? No, the answer is no. That is not positive charge, it is neutral. Because if you remember how p-type semiconductor was formed, it was formed when we had added impurity. We have doped aluminium in the silicon, and in that, because aluminium has only 3 electrons in the outermost shell, so 3 of its electron was bonded to 3 of the silicon atom. 1 electron was left alone, but aluminium has 13 protons. Okay, so there are no less number of electrons. Okay, as far electron and overall electron and proton number are considered. What I'm saying is that proton in the p-type semiconductor, suppose the total number of protons is 100. Okay, all the proton we are including silicon and aluminium, and the total number of electrons are also 100. Okay, so overall it is neutral. Holes are created because aluminium doesn't have that extra electron, so that it can make bond with the 4th silicon atom. Okay, but overall it is neutral. Similar cases in the case of a n-type semiconductor. Overall it is neutral, but it has 1 extra electron. It has also 1 extra proton. It has 1 extra electron, so it is 1 electron is free, that will act as a majority charge carrier. So, okay, so overall it is neutral. It's an important point, you have to remember this. Now what happens due to diffusion? This electron from here will move to this side. Okay, diffusion is occurring. Okay, because electron is moving to this side, so what is happening? It is leaving behind an ionized atom. Okay, electron is moving, so a positive charge will be created here. And in this side, what is happening? Because hole is coming to this side, so there is a negative charge, negative anion is created here. Okay, so let me draw this for you. Okay, so here are majority charge carrier electrons. Some of these are which are near to the junction have this electron have moved here. Okay, and some of the holes have moved to this side. Okay, and this have created ionized atom here. For this side there will be positive charges here. Why there are positive charges? Because electron have moved to that side, and that's why there are ionized atom here, cations. Okay, because 1 electron they have lost 1 electron now. Okay, and in this side there will be negative charges. Okay, and this will create electric field here, positive to negative. There will be electric field from positive to negative. Okay, and there is electric field because of this diffusion. Okay, and this electric field will stop the flow of majority charge carriers. Okay, now you see from this formula the electron. Okay, what is the charge of electron? This is a negative charge. The electric field, what will be the in which direction the force will be acted on this electron? The answer is opposite to the electric field. Okay, so the electric field is in this direction. Okay, let me draw it again. This is the very crucial point. Okay, so there are, this is n-type, inside there are like negative charges, majority charge carrier, and because of the diffusion there are plus charge created here because of the ionized atom, and there are negative charge created here, and there is an electric field here. Okay, and there are majority charge carrier on p side that are holes. Okay, there are holes. Now this electric field, it will not allow further diffusion because it is not, electron wants to go this side, but you know what, in which direction they will the force will acted on them, opposite to the electric field, so they will not able, the electric field is opposing them to move to the other side, while the holes, what is happening to them, they are feeling a force in this direction, in the direction of electric field, so now they are not able to cross this electric field. Okay, so they are not able to cross this depletion region. Okay, and this region is called a depletion layer. Okay, and there is electric field here, and there are, because of this electric field, and there are charges here, there are positive charge here, so positive potential, there are negative charge here, negative potential, a potential barrier is there, and holes and electron are not able to cross this potential barrier. Okay, and a depletion layer is formed here. Okay, this is a very crucial point, depletion rate. I told you how a depletion region is formed. Okay, so now yes, I think I covered this one. Similarly, when a hole diffuses from p to n, the concentration gradient it leaves behind minus at atom. I already told you this. The space charge region on either side of the junction together is known as depletion region, and the electron and hole taking part in initial movement of the group. Okay, so I've already explained you this, and the thickness of this depletion region, let me zoom it for you, then I'll explain it. The thickness of depletion region is of the order of 1/10 of a micrometer. This is the thickness of the depletion region. Due to the positive space charge region on n side of the junction, a negative space charge region on p side of the junction, and electric field directed from positive charge to a negative. Already I have done this, I have explained it to you. You can read it and you can understand. But one interesting thing will happen now. So what will happen? This electric field, it is not in the mood to make the electrons, the majority charge carrier, go to the other side. Okay, so this again I'll draw the n side here, and p semiconductor here. Okay, and you know in the n side there is electrons are there, the majority charge carriers, and p side, p type, there are holes are there. Okay, now here, because of the moment of the diffusion of ions or the electrons and protons, the electron and holes, there was electric field, positive, negative, positive, so there was electric field here. This electric field is not allowing the majority charge carrier to cross this region. But if you see in a semiconductor, due to thermal excitation, there are minority charge carriers, that is in n type there are holes are there, and in p type there are electrons are there. So it is not allowing the electron to go to this side, but it will allow the holes to go to this side. Similarly, it will allow the electron from the p type to go to the other side, and this will give rise to a drift current. Okay, and this is drift due to the minority charge carrier, they will able to cross it. Okay, so we have discussed about two things that are happening during the depletion. One is diffusion of the majority charge carriers, and that will give rise to the depletion region, electric field will be there. Okay, and because of the electric field, it will not allow the majority charge carrier to cross to the other side, but it will facilitate the minority charge carrier to go to the other side, and this will give rise to the drift current. Obviously that is very small because the number of minority charge carrier is very small. As the diffusion process continues, the space charge region on either side of the junction extend, thus increasing the electric field strength. Okay, so as diffusion occurs, now there are the number of electrons, minority charge carrier on both sides are small, and the junction extend. Okay, electric field strengths, okay, hence drift current also extend. This process continues until the diffusion current equals the drift current. Now the equilibrium condition is set in, where the drift current is equal to diffusion current, and now there is no net current. Okay, now everything has stopped. Electron drift current is equal, now become to the diffusion current. Okay, now the loss of electron from the n region and the gain of electron by the p region causes a difference of potential across the junction of the two regions. Already I have told you this, that there is a, because electron, the p side had, because of the movement of the majority charge carrier holes, now it has some negative charge on that side. Okay, and opposite situation on the opposite side, there is the potential difference created, a potential barrier is there. Okay, so this is the barrier potential. Okay, I have already explained all this to you. Okay, so now let's move to the next point, and that is the next topic, that is semiconductor diode. Okay, so what is a diode? So basically a PN junction, when we apply it, we make terminals to it, metallic contact to it, and through the metallic contact we can apply external voltage, so that will become a diode. Okay, so this is a semiconductor diode. So basically it is PN junction with metallic ends. A semiconductor diode is basically a PN junction with metallic contacts provided at the ends of the application of an external voltage. So through the metallic ends, you can see in the diagram, this is a PN junction and there is a metallic contact on the either side, and through them we can apply potential voltage on both the sides. A PN junction diode is symbolically represented. The representation of the PN junction is shown. The direction of the arrow indicates the conventional direction of current. The diode is under forward bias. Okay, so this is when it will be forward bias. I will understand the meaning of forward bias. Actually, what we can do, we can apply battery or voltage in two ways. What we can do, we can apply positive potential or positive part of the battery, okay, to this p type. Okay, and we can apply negative terminal, connect the negative terminal of the battery to the n type. So this condition is called forward biasing, when p is connected to positive terminal of the battery and n is connected to the negative terminal of the battery. This condition is called forward biasing. While there is another condition in which we can connect the p type with negative terminal and we can connect the positive electrode of the battery to the n type semiconductor, and this is the case of reverse biasing. So we have two biasing, and you know what biasing is. Biasing is simply connecting a diode with a battery. So we can connect the battery in two ways, forward biasing and reverse biasing. So normally you see forward biasing, the direction of the current will be from this side. So this is the diagram, this is the symbol for diode. Okay, like you see, this is the p type semiconductor here and n type semiconductor here. Okay, now let's understand what will happen when we'll do forward biasing in PN junction. When an external voltage is applied across a semiconductor diode such that p side is connected to the positive terminal of the battery and n side to the negative terminal, it is said to be forward bias. I already explained it to you. The applied voltage mostly drops across the depletion region, and the voltage drop across the PN side of junction is negligible. Okay, now you see, as I told you, there is a voltage potential barrier here. Okay, due to that movement of the majority charge carriers, there is a potential barrier that the majority charge carrier now cannot cross. So what we when we apply battery to this, okay, so it will also, this is the positive side, it will apply what, electric field in this direction, okay, and the electric field due to the potential barrier is in this direction. So now it will opposite electric field, okay, and if we keep on increasing the voltage, what will happen, the external voltage, if we keep on increasing, you see the electric field, the potential barrier will keep on decreasing. A time will come when the potential barrier will finally it will reduce to zero, okay. So if we keep on increasing the external voltage, okay, external electric field, then this potential barrier will keep on decreasing. So that's what we are doing here, okay. And when it will happen, a large amount of current will start flowing, okay. So now direction of the applied voltage is opposite to the built-in potential. As a result, the depletion layer will decreases, and a question can come in exam, like you must know this, that what will happen if we increase the voltage in forward biasing. So depletion layer region width decreases, the barrier height decreases. Now when the depletion region becomes zero, now there is no barrier, and the electrons, the majority charge carrier, now can go to the other side. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value, and only a small number of carrier in the material, those what happen to be the uppermost energy level, possess enough energy to cross the junction, okay. So if we apply small voltage, okay, the potential barrier will reduce, so only few electron will be able to cross, which are on the outermost energy levels. They will have the energy to cross this depletion region. Still there is depletion region, the current will be small obviously, but if we increase the applied voltage significantly, what will happen, the barrier height will be reduced, and more number of carrier will be have the energy to cross the barrier, that is the decreasing barrier, again the current increases. Due to applied voltage, electron from inside across the depletion region and reach p side. Similarly, hole from p side cross the junction and reach the n side. This process under forward bias is known as minority carrier injection. A term is there, minority carrier injection. You see, as the depletion width decreases, okay, now the electrons, okay, now the electrons, which are the majority charge carriers in n type, and electrons are the majority charge carrier in n type, and in p type holes are the majority charge carrier. Because the this width of the depletion region is decreasing, they are now able to go to the other side, okay. So and electrons are going to this side. The electrons in p side are the minority carriers. So this is called the minority carrier injection. On forward bias, what will happen, minority carrier injection, okay, because from the other side. Another junction boundary on each side, at the junction boundary on the each side, the minority carrier density increases significantly compared to the location far from the junction, okay. Because of this injection, minority charge injection, their concentration will increase near the junction.